All right, guys. Hope you are enjoying your spring break. So here we go. Last mini unit of AP Calc BC, which is Taylor polynomials. So Taylor polynomials is another way of approximating. Okay, we are approximating. If you remember, we did do linear approximations. That was the first thing we ever did in terms of approximations, where we ended up with a formula that we called L of x, and that was equivalent to basically the slope of the tangent, the equation of the tangent line, in the form of y plus m times x minus x1. So this is an approximation just with lines. So if we wanted, and then we did multiple linear approximations. So if we had an equation like an exponential one, right? We approximated by finding the equation of the tangent line at that point. And we used this line right here to figure out what is the value for the point right next to it. And then we moved on and we did the Euler method, Euler. Okay, here we used multiple linear approximations in a table, right? And we did the same thing. We did multiple linear approximations. So we would first find the equation of this tangent line. And then on this tangent line, we would find another equation. And then on this tangent line, we would find another equation to eventually get our approximation. So now what we're going to do is we are going to actually be doing approximations with polynomials of whatever degree we want. Okay, now we can go to infinite degrees, but of course, without a calculator, that's pointless. So Taylor polynomials and approximations. Polynomial functions can be used to approximate other elementary functions such as sine of x, e to the x, and ln of x. So if I told you to tell me what sine of 0.2 is, for example, without a calculator, you really can't do that without having a Taylor approximation. So we'll talk about how that graph looks like in a second. So example 1, find the equation of the tangent line. So we're going to go back to the basics. For f of x of sine of x at x equals 0. Then use it to approximate sine of 0.2. So this was our linear approximations from way back when. Okay, so to find the equation of the tangent line, we obviously need a point and we need a slope. So the point, we already have the x, which is 0. And then to figure out what the y is, we just gotta plug in 0 into the function. So our point in this case is 0 and then f of 0, which is sine of 0, and sine of 0 is just 0. And then to figure out the slope, if you remember, we had to find the derivative. So what is the derivative of sine of x? That's going to be cosine of x. And then once we find the derivative, we plug in that point that we want to approximate around. And cosine of 0 is going to be 1. So now that we have our point and we have our slope, then we can use our point slope form, if you remember. Y minus y1 equals m times x minus x1. Plug it in, plug in what we got. So we got y minus 0 equals 1, x minus 0. So when we rewrite this to get it into y equal form, okay, we got 0 plus 1 times x minus 0. So this form is called the Taylor form. It is a Taylor form approximation. Now, of course, when we clean this up, it ends up being just y equals x. So this is the equation of the tangent line in Taylor form. And this we are using to approximate, okay, L of x, we're gonna call it, because that's our approximation in Taylor form. L of x is equal to x. So we're going to use this to approximate what is sine of 0.2. Now, sine of 0.2 is going to be approximately equivalent to L of 0.2, which is 0.2. Okay. Now, the second part of this question is this an over or under? Is this an over or under approximation of 0.2? Now we know how the graph of sine of x looks like, right? Sine of x starts right here and kind of does one of these. And we know that at 0, okay, it is concave down between 0 and 0.2. So at 0, that is the point POI, but between 0 and 0.2, so between 0 and 0.2, sine of x is concave down, which means, if you recall, that our tangent line approximation is going to be an over estimate. So therefore, L of 0.2 is an over estimate. Okay. So that's our little review. Okay. Now, obviously, tangent lines are polynomials of the first degree. So if I bring over this picture, I'm going to explain. Okay, let's look at this guy right here. So what we did is we found that red line right here, right? That was our linear approximation. That was the equation of the tangent line at 0.2. Now, if you look at the other functions, okay, the more degrees that we take, so for example, if we do a third degree around 0, that's going to be our orange line. Okay, you notice that it follows that sine function, which is the black function, a little bit better. If we go to the 5th degree, that even hugs that sine function a little bit longer. So the bigger the degree, if we go all the way to the 13th degree, which is this light purple line, you notice that it basically is the graph from this point, right, all the way to this point. So the greater the polynomial, the better your approximation. And that is what Taylor approximations are. All right. Now there are, if you need extra, how should I say, my God. All right. If you need extra review on what I just explained, please look up a YouTube video. Okay, it's gonna be a lot better. All right, the equation of a tangent line used in example 1 is called the first degree Taylor polynomial. Taylor polynomials of higher degrees can be used to obtain increasingly better approximations of non-polynomial functions within a certain radius from the center of approximation. So you notice that in our last example, our center was at 0 and our approximation was around 0.2, was 0.2, very, very close to 0. I'm not going to center my approximation at 3 and then try to approximate 0.2. That's pointless. All right, for example 2, on your calculator, y1, graph y1 equals sine of x. And then we're going to use the following windows. So I'm going to pull up Desmos really quick. And I'm going to graph this sine of x from -9 to 9 and from -4 to 4. You don't have to do that on Desmos. We get a pretty good graph. Now in y2, we're going to graph successively, adding an extra term each time. All right. So the first term is what we just solved for, which is the line. Which is x. So you notice that that's our linear approximation from the last example. So at 0.2, the blue line and the red line are close, right? But if I was to zoom in at that point, 0.2, you can kind of see that it's a little bit off, right? It is not a very good approximation. The two lines are distinct, okay? So I'm going to go back in my window, and now I'm just going to keep adding the next term. So the next term that they told us to add is going to be x cubed over 3, over 3 factorial, which we don't have a 3 factorial, so I'm just going to put it in as 6, because that's what 3 factorial is. All right, so there's our cubic function, and you notice that that is going to be hugging the graph even nicer. If I keep going and I add the next term of my Taylor polynomial, which is going to be plus x to the 5th, and I'm going to explain this pattern soon, x to the 5th over 5 factorial, and 5 factorial is 5 times 4, which is 20, times 3, which is 60, times 2, which is 120. We get a 5th degree polynomial that's even closer. So now if I am to zoom in at 0.2, you notice here where did it go? They're basically like the same exact function. So that approximation is going to be even better. And every time you add a degree to your Taylor polynomial, your approximation is just going to be that much better. All right. So what do you notice? I want you guys to answer that. So this is question number 1. Put that into your notes. And then what is y1 of 0? What is y2 of 0? What is y1 of 0.2? What is y2 of 0.2? Remembering that y2 is this. All right. So question, answer those. Y of 0 and y2 of 0. And you can use your calculators to do so. All right, definition of nth degree Taylor polynomial. So if f has n derivatives, that means I can keep deriving at some center c, then a polynomial in this form where this right here is going to be just the constant. Sorry, it's ELL constant. It's the coefficient, right? Which you will notice soon is going to be the same y-intercept as the actual function, plus the derivative times x minus that center, plus the second derivative over 2 factorial times x minus c squared, and so on in this form. Okay, this is the nth derivative at that center, whatever center they are giving us, times x minus that center raised to the nth degree. All right, now it's easy to remember this pattern because even this guy right here is f0c, right? It's the actual function. Technically, this is f0 of c, the actual function, no deriving, times x minus c to the 0th power, which is just 1, over 0 factorial, and we all remember that 0 factorial is just 1. All right, and then same thing with this guy. This is f to the first degree, so first derivative, over 1 factorial, which is also 1, times second derivative, 2 factorial, second degree, nth derivative, n factorial, nth degree. This is called the nth degree Taylor polynomial for f centered at c, named after Brooke Taylor, an English mathematician. Note, a first degree Taylor polynomial is a tangent line to f at c. This is what we did when we were doing Taylor approximations. And then this part of the Taylor polynomial is a coefficient because we will be cleaning this up, right? This right here is going to be the numerator obtained from the derivative at that center term. All right, now with Taylor polynomials, there's the special one, all right? And if the center is 0, then the Taylor polynomial is just whatever f of 0 is times f prime of 0 x, and you notice that we don't have to write x minus 0, even though you'll see me writing it in some of the examples, right? Because x minus 0 is just going to be 0. X minus 0 is just going to be x, sorry, x minus 0 is x. X minus 0 is going to be squared. X minus 0 to the n is just going to be x. This is called the nth degree Maclaurin polynomial. It is still a Taylor polynomial, but it's special, okay? So whenever they say find the Maclaurin polynomial, you have to know that the center is 0. Taylor polynomial basically just expanded on his work and allowed us to be able to center at any point. So Maclaurin not only got his name on a very specific case of Taylor's work, but he also had big hair. So he basically just copied Taylor and said, oh, look, if it's a 0, then you don't have to add the center every single time. For Taylor and for Mach polynomials, you must use a squiggle. If you do not, you will lose points, okay? Because a Taylor polynomial is an approximation. So f of 0.2 is not equal to p n of 0.2. It is not equal. It is approximately equal to that approximation. All right, let's get started. So let's find the Maclaurin polynomial. So right here, they told us it's Maclaurin, so I know that my center is going to be 0. Okay, so it is centered at 0 for a degree n. So what this means is that I am going to be finding 5 derivatives for sine of x. Then I'm going to use that approximation to approximate the value of sine of 1.1. So at the end of all of this, Okay, down here, I'm going to be writing sine of 0.1 is approximately equal to the Taylor polynomial, or sorry, the Maclaurin polynomial to the 5th degree of 0.1. Now that I can put an equal sign because that's what I'm solving for. All right. Then we're going to find the error in the approximation and determine an interval in which sine of 0.1 could actually live. Finally, compare your approximation to the actual value of sine of 0.1. Is it within your interval? So let's get started. And I know that the center is at 0. I need to keep that in my mind. So the first thing we do is we write down our original function, f0 of x, and that is sine of x. And I'm going to find 5 derivatives. So f prime of x is cosine of x, f double prime of x, f to the 3rd degree of x, f to the 4th degree of x, f to the 5th degree of x. I like to write them down before I start deriving, just so I know where to stop. All right, so we got cosine of x. The derivative of cosine of x is negative sine of x. The derivative of negative sine of x is negative cosine of x. Derivative of negative cosine of x is sine of x. Derivative of sine of x again is cosine of x. Once we have found all of our derivatives, we need to figure out what is the value of that numerator at that derivative. So the first one is going to be our constant, our coefficient, right? So what is f0 of 0? Sine of 0 is 0. What is the derivative at 0? Cosine of 0 is 1. And we're going to keep doing that all the way down. All right, negative sine of 0 is 0. Negative cosine of 0 is negative 1. Sine of 0 again is 0. Cosine of 0 is 1. So these right here, okay, are my numerator coefficients. Okay, don't forget about the factorial on the bottom of my Taylor approximation. So now that I have all of my values, it's just a plug and chug. So if you remember the Taylor approximation, and then just build from that. So my Maclaurin polynomial, it doesn't really matter if you call it a Taylor polynomial centered at 0. Taylor polynomial centered at 0 is a Maclaurin, but it's also a Taylor polynomial centered at 0. So my let's do this. My f of x, which is sine of x, is going to be approximately equivalent to my Maclaurin polynomial. And I'm going to write down everything and then clean it up, right? So the first is going to be the numerator coefficient, 0 over 0 factorial times x minus, the center in this case is 0, and that is to the 0th power, plus 1 over 1 factorial, right? 1 over 1 factorial times x minus 0 to the 1. Now, because I know it's a Maclaurin, I don't have to write this 0 every time. I'm just doing it, you know, for teaching purposes right now. Plus, next one, 0 over 1 factorial. Next is 2 factorial. X minus 0 squared. Plus, I'm going to continue right here. Next one, negative 1 over 3 factorial, x minus 0 cubed, plus 0 over 4 factorial, x minus 0 to the 4th. And last is 1 over 5 factorial x minus 0 to the 5th. And there's no dot, 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 because they told us to find it for n equals 5. So this is the 5th degree, okay? Yes, it can keep going, but we don't want to do it for this problem. So now when we clean this up, obviously 0 divided by 1, please remember 0 factorial is 1. 0 divided by 1 is 0 times all of that, which is 1, and that's going to be 0. So I'm just not going to write this down. 1 over 1 factorial is just going to be 1, and that's just going to be x. Plus 0 over 2 factorial is 0, times x minus 0 squared is x squared. Plus minus, that's going to become a minus 1 over 3 factorial x cubed, plus 0 over 4 factorial is 0. What did I just do? I did something, right? 0 over 2 factorial is 0. Who cares what this is? That's going to go away, right? So that should not have been there. Let's fix that. All right, so we were at negative 1 over 3 factorial x cubed. Again, 0 goes away, plus 1 over 5 factorial x to the 5th. Now when we clean this up, this factorial up, we got x minus 1 over 6 x cubed plus 1 over 5 times 4 is 20, times 3 is 60, times 2 is 120. X to the 5th. Now, do you have to go all the way here? No, you really don't. Okay. We could have stopped at the 5 factorial. So now that I have what my Maclaurin approximation is, I can answer my question, right? The question is, what is sine of 0.1 approximately? And that is approximately equivalent to P5 of 0.1. So we can plug in 0.1 minus 1/6 0.1 cubed plus 1 over 5 factorial, 0.1 to the 5th. You plug this into the calculator and you should get a value of 0.99833. So that is our approximation. Okay. And once you put this into the calculator, because that is find the error of your approximation. Now, obviously, to find the error of your approximation, you have to figure out what is sine of 0.1. And sine of 0.1 is, I believe I forgot a 0 here. Okay. Sine of 0.1 from our calculator, which I will put equals, is 0.0998333. Okay, the more decimals you take, and I didn't figure out what those decimals are, let me do it right now. 0.1 minus 0.1 over 6 cubed plus 0.1 to the 5th over 120. This is 833416667. 3341, and this is 41. And you can see that the approximation doesn't really change. Okay, the error is so small, you don't even see it. This is 6,6, this is 6,6. until the number after this. This guy right here is giving me a 6. This one is giving me a 4. So the error in the approximation is very, 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 very small. Okay, pretty cool, huh? All right, example 4. Let's find the Taylor polynomial of degree n equals 6 for the function ln of x. This is centered now at 1. And n equals 6 means we want to find 6 derivatives. Okay, and our center is 1. So our original function is ln of x. And I'm going to write down all the derivatives that I have to find. All right, derivative of ln of x, 1 over x. Derivative of 1 over x is negative x to the negative 2. Derivative of that is going to be 2x to the negative 3. Derivative of this is going to be negative 6x to the negative 4. Derivative of that is going to be 24x to the negative 5. And derivative of that guy is going to be negative 120x to the negative 6. Now I want to find the numerators, right? I want to find the numerators for my Taylor polynomials. And how do we do that? We gotta plug in our center. Plug in the center to each one. So ln of 1, I hope you guys don't mind. I'm not going to write this down, but you can if you want. Okay. ln of 1 is 0. 1 over 1 is 1. Once you rewrite this, right, we got negative 1 over x squared, which is negative 1 over 1, and that's going to be negative 1. 2 over x cubed is going to be 2. Negative 6 over x to the 4th is negative 6. And so forth. 24 over x to the 5th is 24. And negative 120 over x to the 6th, when you plug in 1, is negative 120. So now that I have all my numerators, I can start building my Taylor polynomial, right? So these guys right here are all the numerators for my Taylor polynomial. Let's write it down. So our f of x is ln of x. We are approximating ln of x using P6 of x. And that is equivalent to, let's write this down. So our first coefficient is 0. Eventually you'll get to the point where you are not writing all of this down, right? Over 0 factorial, x minus, now in this case, our center is 1 to the 0th exponent, plus 1 over 1 factorial, x minus 1 to the 1 degree. All right, so remember this right here with this part is the linear approximation. This needs to be a coefficient, which explains why this is raised to the 0. Okay, now in this case, our coefficient is 0. So we'll talk about that. And this part right here is the first derivative, or the slope of that function. All right, let's keep going. Since this is a minus, I'm just going to go ahead and put minus 1 over 2 factorial, x minus 1 squared. Keep going, plus 2 over 3 factorial, x minus 1 cubed. keep going, minus 6 over 4 factorial, x minus 1 to the 4th, plus 24 over 5 factorial, x minus 1 to the 5th, minus 120 over 6 factorial, x minus 1 to the 6th. Let's clean this up. Obviously, this part right here is just 0. This part right here is going to be 1 times x minus 1, so that's just going to be x minus 1. This part is going to be minus 1 over 2, so 1/2 x minus 1 squared. Next one is going to be 2 over 3 factorial, which is 2 over 6, which simplifies to 1/3 over x times x minus 1 cubed. So hopefully you're noticing the pattern already. This is 1 over 1, this is 1 over 2, 1 over 3. Now negative 6 over 4 factorial, 4 factorial is 4 times 3, which is 12 times 2, which is 24. And negative 6 over 24 is just going to be 1/4. And once you see the pattern, and there will be patterns everywhere in this, you know where this is going. I wish I gave myself more room, but it's okay. Minus 1/6 x minus 1 to the 6th. So this is our Taylor polynomial centered at 1 that we're going to use to approximate f of 1.1. So f of 1.1 is approximately equivalent to P6 of 1.1. And once you plug 1.1 into all of this, you should get a value. All right. So I'll let you guys get the value of this, because I did not, and it'll just take more time. So plug in 1.1 minus 1, right, which is 0.1, minus 1/2 times 0.1 squared, plus 1/3 times 0.1 cubed, minus 1/4 times 0.1 to the 4th, and so on. I don't know why I put a factorial here. That should not have been there. And that is going to be our approximation. Now, for ln of x, there's a reason why the center is at 1 and not at 0. You will never have a Maclaurin for ln of x. Okay? And of course, if we were in class, you would tell me why, right? So we know that ln of x has to be greater than 0. That is the domain, right? For ln of x has to be greater than 0. It cannot be equivalent to 0. All right, let's do this again. So this is an example of how they might throw this at you in on the AP exam. So g is a function. What is that function? Who cares, right? It's continuous derivatives, which is the definition for Taylor polynomials. We have to be able to continually derive. And they give you the coefficients of the numerators. Here is the coefficient for g0 of 2, g prime of 2, g double prime of 2, g triple prime of 2. So what does this tell you? What is that 2? Why is that 2 everywhere? That's because that is the center. So this is a Taylor polynomial centered at 2, and they want us to find the 3rd degree, which means we need 3 derivatives. And that's why they gave us 3 derivatives. So we just have to write the polynomial. Now remember that with the Taylor polynomial, I've been writing over 0 factorial and all of that. But remember that when n equals 0, it is a coefficient. So I can just write 3, and I know that that is correct, because 3 over 0 factorial is 3 times x minus 2 to the 0, right? So 3 over 0 factorial times x minus 2 to the 0, that's just going to be 3, and that will be the case every single time. So let's call this our Taylor polynomial of the third degree of x, and that is going to be equivalent to 3. Now, when n equals 1, that is going to be a minus 4 over 1 factorial, but again, I don't need to write that because that's just 1, times x minus center to the 1 degree. Next is my 7, so plus 7. Now here is where the factorials need to start. So this is 0 factorial, 1 factorial, 2 factorial. And this is x minus 2 squared. And then the last one is minus 5 over 3 factorial, x minus 2 cubed. Now, do I need to clean this up? Not really, okay? Unless you know, you have to solve it without a calculator for some value. You might want to clean up 2 factorial. So 3 minus 4 x minus 2. So that right there is our Taylor approximation. Our linear approximation, right? And then it becomes a quadratic approximation with the next part. So this is just 7/2. And then it becomes a cubic approximation. So this is 5/6. And that's all they asked us to do. They just said, write the Taylor polynomial. I don't need to do anything else. I'm done. All right, example 6. So we're going to use the third degree polynomial. So third degree polynomial means n equals 3. So we need 3 derivatives to approximate e of x for x near 0. So if it's near 0, that means my center will be at 0 for my approximation. And then we're going to use that to find this limit. And then we're going to compare it to the actual limit at 0. Okay? So this is part 2. Part 1, I need to write my Taylor approximation to the third degree centered at 0. So n equals 3 and c equals 0. So n equals 3 means start with the original function, which is e to the x. You got to find this derivative 3 times. Now e to the x is easy, which means when it's centered at 0, f of 0 is e to the 0 is 1. What is f prime of 0? 1. What is f double prime of 0? 1. What is f triple prime of 0? 1. All right, so e is kind of nice. So f of x is e to the x, and I'm going to approximate e to the x with the Taylor approximation of the third degree of x. And I'm going to write this down. All right, remember that the first part of a Taylor approximation is just going to be whatever that coefficient is. If it's 0, don't write anything down, but here it's 1. Plus the next term, 1 over 1 factorial is just 1 times x minus 0, and that's x. Y minus 0 because it's centered at 0. Next, plus 1 over 2 factorial, which is 2 times x squared, plus 1 over 3 factorial. I didn't want to write it as factorial. 1 over 3 factorial, which is what? 6 x cubed. Okay. Now, if we wanted to leave these as factorials for the pattern that's coming in a little bit, right? Let's do that actually. So if I wanted e to the x to the 7th degree, you should see the pattern. Starts at 1 times x plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th. And that will be the Taylor polynomial for e to the x. So now that we have found e to the x, I want to find I'm going to use this approximation to figure out what is the limit as x approaches 0 of e to the x. So that's that. So e to the x is this part. So 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. And now I want to subtract 1 from it. And I want to divide it by 2x. So what do you notice happens to the ones? The ones cancel out. So now we are left with x plus 1 over 2x squared plus 1 over 6x cubed. All of that over 2x. Now remember, to plug in 0, I can't have this x in the denominator if you remember limits. But what do you notice? You have an x in each term. So we can factor out an x, right? So if we factor out an x from the top, you are left with 1 plus 1/2 x plus 1/6 x squared. All of that over factoring out an x, 2. So the x's cancel out, and because the x's cancel out, I can continue with my limit approaching 0 and just plug in 0. So we got 1 plus 1/2 times 0 plus 1/6 times 0 squared over 2, and that's just going to be equivalent to 1/2. All right, so the limit as x approaches 0 of this should be approximately 1/2. Okay, should be approximately 1/2. Remember, because we used the Taylor approximation, we need to continue with that term, the squiggles of approximately 1/2. So compare it to the actual limit at 0. Remember way back when, before we knew Taylor polynomials, okay? How would we find the limit of this? This ends up being 0 over 0, so we can use L'Hopital. So when we use L'Hopital, we derive the top and derive the bottom. So this is e to the x, derivative of 1 is 0, derivative of 2x is 2. Now plug in 0, and that's going to be equals 1/2. So our approximation is pretty perfect, okay? All right, so now that we've learned that given a Taylor polynomial, the first term, if you remember, is your y-intercept. The second term, or the second part, the b, comes from the slope. The c came from the second derivative, correct? So if this is a second degree Taylor polynomial for this function x centered at 0, so here we are at 0, what can you say about the signs of a, b, and c? Well, so let's split this up, a, b, and c. So we know that a comes from f of 0. And that is just going to be our y-intercept. And here, our y-intercept is positive, okay? So on this function, the y-intercept is positive. So because f of 0 is the y-intercept, or a comes from f of 0, that's the y-intercept, that's positive. So we can say that a is positive. Now b came from the first derivative at 0. So what is the first derivative at 0? Basically asking, what's the slope at x equals 0, right? And here the slope is positive. So b, therefore, will be positive. And then the last part is c. C comes from the second derivative at 0. And remember, the second derivative is saying, what's the concavity at x equals 0? And in this case, the concavity, it is concave down at x equals 0. Therefore, f double prime at 0 is going to be less than 0, negative. So C will be negative. Now with a question like this, they're not going to go to the jerk function or anything more, because these are the only parts that we can identify without a calculator on a graph. All right, last part. This is actually fun. All right, sometimes we can create Maclaurin polynomials. Key, x equals 0, right? Maclaurin polynomials to approximate functions without having to derive them using Taylor's theorem, but rather by modifying existing polynomials. So here is where the memorization has to come into play. Sine of x, cosine of x, and e to the x are one of the first few that you will have to memorize, okay, and recognize and know how to write over and over and over again. Because from that, we're going to use sine of x to write the first 4 non-zero terms of Maclaurin polynomials for sine of 2x, or this guy, or this guy. Okay? So before we do that, let's actually write out our sine of x. So you can go back in your notes and you can look at that. But you will notice that the difference between sine of x and cosine of x is that sine of x takes the odd nth degrees, so the odd ends, and cosine of x is the even ends. And it does alternate between positive and negative. Okay, so the odd ends, the first nth degree is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. They wanted the first 4 non-zero terms. So this is not saying n equals 4. This means 4 terms. Okay, 1 term, 2 term, 3 terms, 4 terms. And then cosine of x is the evens. And the evens will start at 0. Okay, so it does start at 1. And it's a good way to remember that is we know that cosine's function at 0 does start at 1. Okay, and then sine does start at 0. So that's why the first one's x and this one's 1. All right, and then minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. 1, 2, 3, 4. And then e to the x all right, so e to the x, okay, look back in your notes, but this was the easiest one, right? Starts at 1. So centered at 0. So remember, e to the x looks like this. So starts at 1. And it's just all of them, and they're all positive. So x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. First 4 terms. And now we're going to use sine of x to write our g of x. And basically, instead of this x, so instead of this x, this x, this x, this x, we're going to plug in 2x. So parentheses minus parentheses cubed over 3 cubed, right? Plus parentheses to the 5th over 5 factorial minus parentheses 7 over 7 factorial. And inside those parentheses, we remove the x and we plug in 2x, 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 2x. And that's it. And you can clean this up if you wanted to, or you can keep it just like that. Okay. So that's for that one, for plugging in to x. Now this one is basically saying multiply cosine of x by x. So all we want to do to get our g of x, which is x times cosine of x, is we're literally just going to multiply all of this by x. So x times 1 is x. X times this part is going to be x cubed over 2 factorial plus x to the 5th over 4 factorial. Be careful. Minus x to the 7 times over 6 factorial. And we're done. Now the last part, there's 2 things. We want to change this x, right? So anytime there's an x, we're going to plug in x squared, and we want to multiply the whole thing by 4. So g of x is going to be 4 e, and instead of this x, we're going to be plugging in x squared. And that is going to be approximated by, all right, bear with me. So we're going to multiply everything by 4. And then in here, there's no x with the 1, so that's just going to be 1 plus parenthesis squared over 2 factorial plus parenthesis cubed over 3 factorial plus parenthesis 4th over 4 factorial. And what's going to go into that parenthesis? X squared, x squared, x squared. And then the last part is, let's clean this up. So x squared squared, I'm going to do it in 2 steps, or we can do it in, yeah, we'll do it in 2 steps. So 1 x squared squared is going to be plus x to the 4th over 2 factorial plus x to the 6th over 3 factorial plus x to the 8th over 4 factorial. And then the last part, I'm going to distribute the 4 So we got 4 plus 4/2, which is 2x to the 4th, plus 4/6, yep, 6, because that's a 6. So that's going to be 2/3 x to the 6th plus 4 over 4 factorial. So that's going to be uh 4 over 4 factorial is 2 times 2 is 6. So it's going to be 1/6 x to the 8th. And that's it. So key is to have these 3 original ones memorized. You could possibly have a quiz on this when you guys come in on Monday, just for kicks, right? All right, good luck.